Alright, chemistry class, let's look at chapter 10, which is all about the mole and mass-mole relationships and mole-volume relationships. Remember, let me just put down really it's all about the mole here. Okay? So chapter 10, remember we had a relationship between the mole and mass and number of particles and volume. So I will give you this relationships, all these relationships for the test, but just to review here, if you are going between mass and mole, if you know the mass and you want to find out how many moles that is, you would then divide by the molar mass, and we get the molar mass straight from the periodic table. If you know the moles and you want to find out what the mass is of that, you would multiply by the molar mass, which is the mass for 1 mole. If you're going between mole and particles, if you know how many moles you have, you would multiply by Avogadro's number, 6.022 times 10 to the 23rd. In the other direction, you would divide by that same number. Okay? Remember, a mole is just a number. A mole is just 6.022 times 10 to the 23rd, like a dozen is 12. It's a very helpful number because it is that number that gives us the mass in grams of a mole of something, and that numerical value is the same as the atomic mass for elements on the periodic table. Okay, so we just have to look at the periodic table to find the molar mass of something. If the item, the species, the element, the compound is a gas, then we can find a relationship between moles and volume, because at STP, remember STP is standard temperature and pressure. STP means 0 degrees Celsius and 1 atmospheric pressure. At STP, the volume of a mole of any gas is going to be 22.4 liters. So if you know how many moles you have and you want to find the volume of that, you would just multiply by 22.4 liters. If you know the volume and you want to find how many moles that is, you would divide by 22.4 liters. Okay? So this relationship, this diagram is showing the relationships between all of those different quantities. Okay? Let's do a few problems together. And as I do them, I'm not going to do them completely. I'll just kind of set them up for you, and then you can finish them by doing the calculation once you understand how to do it. Okay? So we're looking in the book on page 338, and I'm going to start with number 52, which says how many hydrogen atoms are in a representative particle of each substance. So I'm just going to do a few of these with you, and then you could do the rest. So this first one is aluminum hydroxide. So this is just looking at, do you understand how to read this formula? And it's asking how many hydrogen atoms. Well, you need to understand that when something is in parentheses like this with the subscript outside, that applies to everything. So here is aluminum hydroxide. That's the formula for aluminum hydroxide. This OH is tripled. So that means you have 3 hydrogen atoms per compound. Okay? That's all you're doing for that one. So you can do the rest of them. How many hydrogens are in each compound? Try B, C, and D for number 52. Okay. Number 55 says which contains more molecules? 1 mole of H2O2, 1 mole of C2H6, or 1 mole of CO. It says which contains more molecules? Well, a mole of this, or a mole of this, or a mole of this, those molecules, if you have a mole of each, they're all equal. Doesn't matter. They all contain 6.022 times 10 to the 23rd. It's not asking how many hydrogens or how many carbons or how many How many atoms? How many molecules? Well, if this is a mole of molecules, that's a mole of that molecule, that's a mole of that molecule. A mole is just a number. That's it. Okay? Now in number 56, it's asking, what about atoms? Which has more atoms? So if you have 1 mole of H2O2, or 1 mole of the same compounds here, C2H6, or 1 mole of this carbon monoxide, which has more atoms? Well, this one has 4 atoms per molecule. This one has 8 atoms per molecule. Okay? This one has 2 atoms per molecule. So this has 8 times a mole. So this has 8 moles of atoms. This has 4 moles of atoms. This has 2 moles of atoms. So this one has more atoms in it. Okay? Okay, number 57 says, find the number of representative particles in each substance. Okay? Let's take number 57 here. I'll do one of them with you, and then you can do the others. So it says, find the number of representative particles. So if we have 3 moles of tin, okay? Well, what you're going to do is, you're going to take, if you have 3 moles of tin, you're going to take 3 times Avogadro's number, 6.022 times 10 to the 23rd. You do that on your calculator, and you have the number of particles that are represented in 3 moles of tin. Okay? For B says, what if you have 0.4 moles of KCl? Okay? So in this one, if you've got 0.4 moles, well, 0.4 times Avogadro's number, 6.022 times 10 to 23rd. That's how many units of that you have. Okay? Alright, let's jump down to number 60. It says calculate the molar mass. This we get straight from the periodic table. Now, I'm going to let you do the calculation. I'm going to let you look up the numbers on the periodic table. I'm just going to set it up for you. Okay, I'll do one of these with you, and then you can do the rest. So if we have H3PO4, what you're going to do is you got 3 hydrogens in this, so you take 3 times 1, which is the molar mass of hydrogen. You're going to take, you have 1 phosphorus, 1 times the molar mass of phosphorus. I'm not sure what that is, so you're going to look up this molar mass of phosphorus. Look at that number. 4 oxygens, 4 times 16. I know the molar mass of oxygen. You get that number, and then you add all of these up, and you get the total. And that is going to be your molar mass for this particular compound. That's phosphoric acid. Okay? B is the same thing. N2O3. 2 times 14. I know the molar mass of nitrogen is 14. 3 times 16. Molar mass of oxygen is 16. Find those values and then add them up to get the total. And you can do that. Okay? Okay, let's look at number 61. It says calculate the mass of 1 mole of each of these substances. Same thing. If it says you're going to find the mass of 1 mole, you're finding the molar mass. It's exactly the same thing. So A says silicon oxide. So you're going to take 1 silicon, whatever the molar mass of silicon is, look it up on the periodic table. You get 2 oxygens, 2 times 16, that number, and then just add those 2 numbers together to get your final molar mass. Molar mass is in grams per mole. Okay? Grams per mole. Okay, now what if we have to go between moles and mass? That's where we have to use the molar mass to convert. So let's look at number 62. Okay, find the mass of each substance. So I'll do a couple with you, and you can do the rest. A says find the mass of 1.5 moles of C5H12. Well, if we have 1.5 moles, what's the mass of 1 mole? We got to get that from the periodic table. So the molar mass of this is 5 times 12, that's 60. 12 hydrogens, 12 times 1, that's 12. Your molar mass is 72 grams per mole. But you actually have 1.5 moles. So you can take 1.5 times 72 to get the mass of those 1.5 moles. Okay? This would be your answer. Let's do one more together. Let's do B. It says find the mass of 14.4 moles of F2. So you look on the periodic table, look for F. There are 2 of them. It's F2. So 2 times the molar mass of fluorine is going to give you the molar mass of F2. Then you're going to take this number and you're going to multiply that by 14, 14.4, to get the molar mass of 14.4 moles of F2. Okay? All right, you do the rest of those. Let's look at number 63. It says calculate the mass in grams of 0.25 moles of each of the following compounds. Again, it's the same thing. So if we're going to find for A, we have sucrose, C12, H22, O11. We have to find the molar mass of sucrose. Well, that's 12 carbons, 12 times 12, plus the 22 hydrogens, plus the 11 oxygens. You have to find that value, and then that would be the mass of 1 mole. It's the grams per mole. But you don't have a full mole. The problem says you only have 0.25 moles. So you take that number times, you take the 0.25 times your molar mass, and you find the mass of the 0.25 moles of sucrose. Okay? And then you can do B and C. Oh, not 64. Let's do 65. Now in 65, we're going the other direction. It says, how many moles do we have? Well, let's look at the first one. If you've got 15.5 grams of silicon oxide, well, is that a full mole? Well, we have to find out. Let's look at the periodic table. You look for silicon on the periodic table. You have 1 silicon, so 1 times its molar mass, right? Whatever that number is. You got 2 oxygens, 2 times 16. You add these numbers together. That's your molar mass. That's going to be your grams per mole. But you may not have exactly that amount. Whatever this molar mass is, you have 15.5 grams. So is that a full mole? I don't think so, because that's not that number. It's less than that number, I'm sure of it. So you don't even have a full mole. So you're going to take your 15.5 grams and divide by the molar mass. Or in other words, you could look at it this way. You're multiplying by the 1 mole per the molar mass, the mass in grams, whatever that molar mass is. Okay, whatever this number is. So you can take your 15.5 divided by the molar mass to find out how many moles you have. Okay, you can do that, and then you can do some others there to practice. Let's look at 66. Is just seeing if you know. It says, what is the volume of 1 mole of any gas at STP? So at STP, volume of 1 mole of any gas is 22.4 liters. Done. Okay? So that being known, now we can go and say number 67. Calculate the volume of each of the following at STP. So these are all mole amounts. All you have to do is you got to take moles times 1 mole is 22.4. So 2 would be double that, 3 would be triple that. So take the number of moles times 22.4 on every single one of these. On every single one in number 67, they give you mole amount, mole amount, mole amount. Just take the number of moles times 22.4. And you'll have all the answers for 67. Okay. Oh, number 68 is a good problem. It says a gas has a density of 0.902 grams per liter at STP. What is the molar mass of this gas? Well, molar mass is grams per mole. Okay? So all we got to do is we got to convert. This is given to us in grams per liter. We want grams per mole. So we have to convert the liters to moles. How do we do that? With 22.4. So I would write it like this: 902 grams for 1 liter. And then we use this relationship. For any gas at STP, it is 22.4 liters for a mole of particles. So I want to convert liters to moles. So I want to cancel liters. So I know it is 22.4 liters for 1 mole. So I'm going to take 0.902 times 22.4, and that's going to give me my answer in grams per mole. Okay? Okay, 69. Now we're going to do the opposite of what we just did in 68. It says, what is the density of the following gases at STP? So, C3H8, the molar mass here, I'm going to find the molar mass. So I've got my 3 carbons, that's 36, my 8 hydrogens, that's another 8. So that's a total of 44 grams per mole. Now just look at the units. 44 grams for 1 mole. Well, I want density, which is grams per liter. So I want to convert moles to liters. I want moles to cancel, and I know that 1 mole is 22.4 liters for every gas, for any gas. So 44 divided by 22.4 is going to give me my grams for 1 liter. Okay? You can do the rest of those for number 69. Alright, then we got into percent composition. So number 71. What is the percent composition of the compound formed when 20 or 2.7 grams of aluminum combine with oxygen to form 5.10 grams of aluminum oxide? Okay. Alright, we have percent composition of the compound formed when... Okay, percent composition is by mass. So if we'll look here, it says we've got 2.7 grams of aluminum, and it's going to combine with a certain amount of oxygen to give me what? A total of 5.10 grams of the aluminum oxide. Okay? I think aluminum oxide is that, if I'm not mistaken. Okay? So, all you have to do here is look. Conservation of mass tells me that if I've got 2.7 of aluminum, then the rest of it has to be oxygen to make up this total. Okay? So that's got to be, what, 2.4? It's got to be 2.4, right? Give me my 5.10, give me 5.10. So, when I do that, now I realize that my percent composition of the aluminum is my 2.7 out of the total of 510 times 100. And my percent oxygen is going to be the 2.40 over the total times 100. Okay? Same thing with 72. Number 72, they tell you that you've got 13.3 grams of iron, and that's going to combine with 5.7 grams of oxygen Well, that means the total is going to be the sum of those two. So for iron, it's going to be the 13.3 over the total. Okay, times 100. And then for oxygen, it's going to be the 5.7 over the total times 100. Okay. Number 73 says calculate percent composition of each compound. So here we're going to do the entire problem. So in this one, what we want to do is we're going to find out how much of this total compound is hydrogen, how much of it is sulfur. So I've got hydrogen, which is my molar mass of hydrogen is 2 times 1. Sulfur, you can take 1 times the molar mass of sulfur, look it up, whatever that number is. Okay, you need your total. So you're going to get the total of these two numbers here. Then the percent composition is going to be 2 over the total for hydrogen times 100. And then sulfur, it's going to be this number, okay, over the total times 100. It's always the mass of the element in the compound over the total for that entire compound. The mass of this element over the total, okay? All right, 75 says, which of the following compounds has the highest percent of iron? Well, all you're going to do is you're just going to take each of these, when you do each of these, iron chloride. So this one, you're just going to take the molar mass of iron, right, over the total times 100. You don't have to worry about the chlorine. And for B, you're just going to compare it, same thing. Take the iron, the mass of the iron, you have 1 iron, over the total, you got to find the total, times 100. And you're just comparing all of those. Okay? Okay, number 76. All right, this time we're not given the formula and then find the percent composition. We want to find the formula. So number 76 says, what is an empirical formula? And which of the following molecular formulas are also empirical formulas? So let's look at this one here. Oh, okay. So 76, it just says, what is an empirical formula? Empirical formula is the simplest ratio of the elements in the compound. So all you have to do for A, B, C, and D is look and see which one of those is in the simplest ratio. Okay? So C5H10O5, that's not the simplest ratio. The empirical formula for this would be CH2 and O. That's the simplest ratio. This is in a 1 to 2 to 1 ratio. So you just have to look and see which one of those are already simplified, which ones are not. Okay? And number 78, you're just comparing them to see, do they have the same empirical formula? So C2, this is A, C2H4O2, and then compare that to C6H12O6. Are these the same empirical formula? Yes, this is a 2 to 4 to 2, which is a 1 to 2 to 1 ratio, and this is a 1 to 2 to 1 ratio as well. So these both have the same empirical formula. Okay? 79. What is the molecular formula for each of the compounds, each compound's empirical formula, and mass formula? Okay. All right, so this one here, and this one, 79, says what is the molecular formula? So they give us in A, the empirical formula is CH2O. But that mass is a carbon, which is 12, 2 hydrogens, which is 2, and an oxygen, which is 16. That's 14, well, that's 30, right? But it says the actual mass of our compound is 90, which is 3 times that. So our actual formula must be C3H6O3. Just multiply all of those by 3. Okay? All right. Let's practice a little bit on finding the molecular molecular formula and the empirical formula, let's go to actually, I'd like to do let's do number 88, okay? Number 88 says determine the empirical formulas of compounds with following percent composition. So remember the trick here is you assume 100 grams. So for number A, or letter A, it says you have 42.9% carbon, which is going to be 42.9 grams if I have 100 grams. And 57.1% oxygen, and that's going to be 57.1 grams if I have 100 grams. Okay? So the nice thing about assuming 100 grams, your percentage is easy to convert to grams by multiplying by the 100 grams there. Okay? And then all you do is, if I've got 42.9 grams of carbon, 57.1 grams of oxygen, then what I want to do here is I am going to take and convert these. So I've got 42.9 grams of carbon, 57.1 grams of oxygen, and I know that that is going to be then, oh, I want to find out how many moles that is, okay? Sorry, I had a little lapse there. So I'm going to divide this by 42.9 grams is how many moles? I divide by 12. 57.1 grams of oxygen, I divide by 16. And I'm going to get a value there. Okay? So 42.9 divided by 12. Here, we'll just go ahead and see if we can find this out here. Divided by 12. 3.575. Okay? And then you're going to take the 57.1 divided by 16, you're going to get a value there. Okay? Uh, 57.1. Okay? So that's 3.5. That's about the same value. So that's kind of nice. 3.5 something, 6.1. And then you divide each of them by the smallest. Well, they're about the same. So you're going to get a 1-to-1 ratio here. So this is carbon monoxide. Okay? All right. Microphone what he says. Okay. Let's look at just one from number 89. Okay. Now, in this one, it says determine the molecular formula for each compound. In 89, you're going to do exactly the same thing we did in number 88. You're going to assume 100. So it says you've got 94.1% oxygen and 5.9% hydrogen. You're going to do exactly the same thing. Assume 100 grams. So if that's the case, you've got 94.1 grams of oxygen and 5.9 grams of hydrogen. Take the 94.1, divide by its molar mass, which is 16, divide this by 1, no big deal. So once you get those values, then you're going to divide each of those by the smallest value and get your formula. Okay? But you're going to compare that formula then to, it says the molar mass is 34. Okay, again, let's just go ahead and do these. Okay, 94 divided by 16. So you get 5.875. Okay, so this is about a 1. This is the same thing. So this is going to be about 5.875. This is about 5.9. So you get the same value. If I divide these by the smallest value, I'm going to get a 1 and 1 for both of them. So this is OH. Okay, 1-to-1 ratio. But it says the molar mass is 34. This molar mass is 16 plus 1. It's 17. Okay? But the actual molar mass of what we're looking for is 34, so it must be double. So the formula we're looking for is O, actually it's going to be H2O2. Right there, it's that. It's hydrogen peroxide. Okay? All right, we're going to leave it there. If you got questions, please let me know. You can check these answers with me in the teacher edition. If you have questions, bring them up in class or let me know what you're thinking, and I'm happy to help as always. Okay?